Before I start to explain how the ultrasonic sensor works in detail, I thought it would be beneficial to explain what sound is. So, at its most basic form, sound is regions of high and low pressure that travel through the air. It is important to note that even though we talk about waves and we talk about moving and expanding sound waves, it's not that molecules are actually going through the air. Molecules only vibrate around the central point, as you can see here in slide 1. Particles oscillate around a central position. Molecules do not travel across the room with sound. Energy travels. Now, another kind of misunderstanding is that usually sound waves are represented as transverse waves. Okay, as you can see here, these waves are going up and down, okay? And usually people show sound waves as transverse waves, but really sound waves are not transverse. They do not go up and down. They're longitudinal waves, okay? They go, let's say, just on the x-axis, the high pressure, low pressure, high pressure, low pressure. They do not go up and down. The problem is that it's very hard to represent and show on a graph a longitudinal wave. That's why they show these sound waves as transverse waves, where the top is the high pressure and the bottom is the low pressure. Okay, let's see how these waves are actually made. So here we have a diaphragm. Now you could see here in slide 1, the diaphragm is going out, okay, it's pushing out. Now what happens when the diaphragm pushes out? It compresses the air in front of it, like you can see here. Now, when it compresses the air in front of it, this air now has high pressure. And always in nature, high pressure wants to go to low pressure. So this high pressure air pushes outwards and pushes the air in front of it. And that air now becomes high pressure. So that air pushes the air in front of it. And so on and so forth. And that's how we have that high pressure wave continuing on. Now a moment later, the diaphragm gets sucked in or moves in. What happens when it moves in? It creates a void. That void is low pressure. So now we have high pressure outside of the void. It wants to get sucked in to the low pressure. And that sucks the air in front of it, which sucks the air in front of it, which sucks the air in front of it. So what we get here is the diaphragm moving in and out, as we see in slide 3. The diaphragm is moving in and out, which is creating these regions of high and low pressure. So when the diaphragm goes out, we have high pressure, and it pushes the air in front of it, which pushes the air in front of it. And when it gets sucked in, it sucks in the air in front of it, which sucks in the air in front of it, okay? And depending on the speed of the diaphragm, that will determine how much regions of high and low pressure we get, okay? So that's how a basic speaker works. That's how a basic sound machine works, right? It just creates these high-low pressure regions. When we learn science, they talk all day about frequency. What's the frequency of this? What's the frequency of that? Well, what is frequency? What is sound frequency? Frequency just means how many cycles happen each second. Okay, so if we're talking about sound, we care about cycles of high and low pressure. So frequency will tell us how many of these cycles of high and low pressure do we get each second. If you would look in figure 1 at the diagram, you would just see these high pressure and low pressure regions. So these are sound waves, okay? And depending how many occur every second will determine the frequency. Okay, now the unit for frequency is hertz, as you see here. 1 hertz just means 1 cycle per second. So if I say, hey, this sound wave is 1,000 hertz. 1,000 hertz just means there's 1,000 cycles of high and low pressure each second. Okay, if you would look at figure 2, you would see that our ears cannot hear each frequency of sound. Our ears could hear from around 20 hertz to 20,000 hertz. Anything above that is ultrasonic. Our ears cannot hear it. It's still there. There are still oscillations of high and low pressure, but our ears cannot hear it. Now, you could ask yourself, what do we care? What do we care about frequency? What does it matter? Well, in sound, the frequency determines the pitch of the sound. So if the frequency is high, okay, like here on the bottom, you see a high frequency, a lot of waves every second, they'll give us a high pitch, okay, a squeaky pitch. If we have low frequency, like you see on the top, it will give us a low pitch or a bass pitch, okay? It does not change how loud the sound is. It only changes the pitch. So if both of them have the same amplitude, and I'll explain in a moment what that is, the frequency only changes the pitch. Okay, now what is amplitude and how do we determine how loud the sound will be? Well, if you look in figure 4, you would see the 2 graphs. Both of them have the same frequency. But you can see both of them have these 3 squiggles, okay? So they're moving at the same speed, okay? So both have the same frequency. Well, one has a higher pitch. Pitch is the difference between the high pressure and low pressure regions. So if you look here in figure 1, you can see, yes, there's high pressure and low pressure regions, but they're very close to each other. They're just wiggling around the neutral point, around the normal pressure in the area, okay? Just small swiggles above and below. But on the bottom picture, you would see, yes, it's the same frequency, but wow, the high is really high and the low is really low. Okay, so the difference is much greater. That is amplitude. And amplitude is the factor that determines how loud the sound will be. We always hear about speed of sound. Everyone heard about it. Well, what is the speed of sound? How fast is it in the air? Well, it depends. It depends on the temperature of the air. In cold air, we have a low speed of sound. In warm air, we have a high speed of sound. The rule of thumb is that the speed of sound is 331 meters per second at 0 degrees Celsius. For every additional degree, we add a 0.6 meters per second. Okay, so for example, if let's say it is 15 degrees outside, well, we would do 15 times 0.6, okay, and then we would do plus 331. So we would have 340 meters per second. If let's say it is 23 degrees outside, then we do 23 times 0.6, okay, plus 331. So we would have around 344.8 meters per second, okay? That is the rule of thumb. That's what I use in my tests, and it's pretty accepted. Okay, here on figure 3, you could kind of see just at 0 degrees, we have 331, 30 degrees, it's 349. That's how it changes. What does the temperature have to do with the speed of sound? Okay, why should one affect the other? Well, temperature is the average kinetic energy in the air, okay? So the hotter it is, the more kinetic energy there is, meaning the molecules are moving quicker. Well, quicker moving molecules are easier to push, okay? And well, sound travel is the pushing of air. So the hotter it is, the easier it is to push, okay? So if we go back to our diaphragm slide, right? Diaphragm goes out, we have, this high pressure region. High pressure region wants to go out to the low pressure in front of it, so it pushes. Now, if these regions are hot, they have more kinetic energy, okay? So they're easier to push. So yeah, that's the explanation for that. And again, remember, when we talk about the speed of sound, it's not that the molecules are moving through the air at this speed. The molecules are just vibrating around a central point, and the energy is moving at this speed. Okay, next slide. How fast does sound travel in different materials? Okay, so we're only really accustomed to the speed of sound in air, right? That's we echoes and talking to our friends. We don't really think about speed of sound in other materials. But other materials have a different speed of sound, right? If air, it's around at 20 degrees Celsius, it's around 343 meters per second. In water, the speed of sound is 1,480 meters per second. That also depends if it's salt water or not. But that's much quicker. It's around 5 times quicker than the speed of sound in air. So if we have a submarine that sends out an ultrasonic wave, okay, to determine, position or distance or obstacles in front of it, the sound will travel much quicker, okay? That's very important to understand. If you look at steel, it's around 5,000 meters per second, okay? So it's around 15 times quicker than the speed of sound in air. Now, why do different materials have a different speed of sound? Well, it depends on how dense the molecules are and the elasticity. So steel is very elastic, right? That's like the ultimate elastic material. So the speed of sound is very quick. If you look here in figure 3, there's a great example. So let's say we have a train track and we have someone that puts his ear on the train track, which is made out of steel. And say he has a friend next to him, okay, which is not putting his ear on the train track, and a train comes, who will hear the sound first? Well, the person that's putting his ear on the train track will hear it much before the friend that is not putting his ear on the train track, because the speed of sound in steel moves at 5,000 meters per second, so 5 kilometers per second. It's like 15 times quicker than the speed of sound in air. So he will hear the train coming, okay? The train on the track is creating, a very loud vibration, but it takes time for that vibration to go through the air. It also takes time to get through steel. Just through steel, it's much quicker, okay? So that's just, I think, a great example to explain the difference. Okay, now of course ChatGPT had to add danger, do not put your ear on the real train tracks. Now I did not tell him to do that. I did prompt this example. I say write this example. He had to add that, but I guess that's just very AI-ish. Okay, figure 4. How fast would sound travel in space? This is kind of like a trick question that everyone asks. Well, the answer is it will not travel at all, right? Because for sound to travel, we need vibrations of high and low pressure, okay? So to have these vibrations of high and low pressure, we need something. We need something to vibrate. Space is a vacuum, right? It's the ultimate vacuum. So sound cannot travel, okay? So I said that the sound wave transports energy, okay? Now this is very important because soon we'll start explaining the ultrasonic sensor, and we have to understand that sensor works on energy, okay? It works on detecting the energy that's coming back from the sound wave, okay? So how much energy does sound carry? Well, it's surprising, but not much, really not much. So if you would take, for example, 0 decibels, which is the threshold of hearing, right? It's the lowest amount that our ear could detect. It has 1/trillionth of a watt meter, okay? 1 times 10 to the negative 12th power of a watt meter, okay? Now, if we would go to loud sound, for example, 100 decibels, okay, 100 decibels is around the sound that a motorcycle up close makes, or a very loud power tool is around 100 decibels. Now, 100 decibels is not 100 times 0 decibels, it's 10 billion times, okay, because decibels is logarithmic, so 100 decibels is 10 to the 10th power, okay? Now, the amount of energy 100 decibels will have is 0.01 watt meters. Again, not a lot of energy, and this is a loud sound. Okay, now this is very important. And this is the amount of energy at the core. So if we look at figure 2, right, and we look here, this small dot, this is where the energy is being produced, okay? The diaphragm, the motorcycle, the power tool, this is where the energy is being produced. Now, as it moves on, okay, it kind of expands as a sphere. Okay, now I know earlier I showed that sound waves is these high and low pressure, yeah, but sound does not travel in these thin strips, okay? Sound expands as a sphere. Okay, so it starts here in this little dot, and then it expands, okay, unless there's something that doesn't let it expand, like a wall. But if there isn't something that doesn't let it expands as a sphere, so it expands 3D in all directions. This is important. Why? Because if, let's say, we have this ball, okay, let's say this ball has 1 unit of energy for every centimeter, okay, whatever that unit of energy is, okay, for every centimeter of the ball, okay. Let's say we double the distance, okay, so we see we double the radius, we double the distance, now we have this sphere. How much energy will be in every centimeter of this sphere? Okay, we double the distance. So here we had 1 for every centimeter in the small sphere. We double the distance. How much will we have now in the big sphere, in the new sphere, for every centimeter? Well, the answer is we'll have a quarter, not half. You would think a half. We double the distance, well, we should have half. No, we have a quarter. Why is that? Well, to understand that, we have to understand the calculation of to determine the area of a sphere. Okay, so if you would look here, you would see area equals 4 times pi times radius square. What does that mean, radius square? That means if we double the radius, we quadruple the area, okay? So it's times 4, okay? So if in this small ball we had 1 unit of energy for every centimeter, now if we double the distance, we have a quarter, okay? This is very important for ultrasonic sensors because for ultrasonic sensors to work, again, we need that energy coming back, and I'll explain soon how that works, but the sound wave now is going there and back. So if, let's say, we're a meter away from something, and there's 1 unit of energy for every centimeter, okay? If we double that distance and we need it to go there and back, we'll get a 16th of the original energy. Why is that? Because we lose a quarter from doubling the distance in one direction, and then we get a quarter of the quarter for coming back, okay? So we're left only with 16th of the energy. Now, usually we're left with even much less than that. Okay, this is only the energy being lost from the sphere expanding. But really, in the real world, we also lose energy from the air absorbing some of that energy, and especially in high frequency. High frequency gets absorbed much, much more, okay? Because high frequency means that the wavelength is much smaller, so it can interact with the air much better, okay? So the air absorbs that energy much more, okay? So the 16th of there and back is without this absorption, okay? So it's very important to understand this and why there'll be a limitation on the distance this ultrasonic sensor could work, because we need to go there and back, and we need to still have enough energy to be able to detect. I thought it would be cool to wrap up this section about sound waves to explain how our ear detects sound. Well, if we would look inside the ear here in figure 1, we would see the outer ear. And then inside, there's the eardrum. The eardrum is just a diaphragm, okay? It's just like a flexible piece of skin that on one side, here on the inner side, is the regular pressure outside. And in the outer side is open to the air from outside. It's open to the sound waves, okay? So if there's no sound, then the pressure that comes into the ear is the same as the pressure that's in the ear itself, okay? That's in the inner part of the ear. So the diaphragm doesn't move. Once sound starts, right, and we know that sound waves is just regions of high and low pressure. So once we get those regions of high and low pressure coming into the ear, if, say, the high pressure region comes in, okay, it pushes the diaphragm in, right, because we have high pressure. High pressure means higher than the ambient pressure, okay? So it pushes the diaphragm in, like you see here, okay? Then low pressure comes right after that, and it gets sucked in, okay? So the diaphragm goes the other way, because here we have normal pressure, and here we have lower pressure, lower than normal, so it gets sucked in, okay? So if we have a sound wave which has high and low pressures, the diaphragm in the ear, or the eardrum, gets moved in and out, in and out, in and out. Now, depending on the frequency of the sound, right, the eardrum will go quicker in and out or slower in and out. Now, in some complicated way, which I don't really understand, that in and out motion of the eardrum is turned into signals that our brain can understand, and we could, perceive sound. And it's amazing, but that's how it works. So again, we just have the high and low pressure coming into the ear. That pushes the diaphragm in and out, and that turns into brain signals to pick up sound. Before we can understand how the ultrasonic sensor works, we have to understand one more piece of physics. That is the piezoelectric effect. What is the piezoelectric effect? Well, piezo means stress. The piezoelectric effect tells us that if we put stress on a crystal, there'll be a voltage across the crystal, okay? So if you would look here in figure 1, here on the left, we have a crystal, no stress is applied on it, and therefore no voltage, okay? So we're measuring the voltage on the plates. No voltage, no stress. If we compress the crystal, okay, so we're applying a force, okay, a stress on the crystal, we could see that there's voltage on the plates, okay? And if we put a tension, okay, so we pull the crystal, we have also a voltage, just the opposite voltage, okay? So compression will give us a certain voltage and tension will give us the opposite voltage, okay? So again, the piezoelectric effect tells us that if we apply a mechanical stress on a crystal, we'll get a voltage. Now, what happens if you apply a voltage to a crystal and not a stress? Well, the same thing happens. Let's explain this. Let's say we have a crystal. Okay, here on the left side, you see a crystal, no stress, no voltage, nothing happens. Now, here in the middle, we're not applying a stress, but we're applying a voltage, meaning we have a battery here that's applying a voltage across the plate. That will deform the crystal. Okay, we'll explain in a moment why, but it deforms the crystal. And if we change the polarity, okay, we change the direction of the current, okay, so here's now minus and here's plus, we will deform the crystal in the other direction, okay? So if you can see, if we have plus on top and negative on the bottom, it gets squeezed, and if we have minus on top and plus on the bottom, it kind of like becomes longer, okay? So what would happen if, for example, we would give an AC current and change it, let's say 1,000 times a second, okay, at 1,000 hertz. Well, the crystal will change its shape 1,000 times a second, okay, or vibrate at 1,000 times a second. This is the source for the ultrasonic sound in the sensor, okay? So if the ultrasonic sound, for example, is at 40,000, hertz, okay, or 40 kilohertz, then we give an AC voltage to the plates at 40,000 hertz, so it's changing 40,000 times per second. That will deform the crystal 40,000 times per second and vibrate, and that vibration creates a sound, okay? So very important to understand. So just to recap, we have the regular piezoelectric effect. So if we squeeze the crystal, it creates a voltage, okay? And the second effect is that if we put electricity across the crystal, okay, on the plates, it will also deform the crystal, okay? And changing the electricity, the polarity, will change the shape of the crystal. Okay, now why is this and how does this work? Okay, so to understand this, we have to understand that, let's see, at least a quartz crystal is made out of silicon and oxygen, okay? Now, both silicon and oxygen are nonmetals. The way nonmetals connect is by covalent bonds. What is covalent bonds? Covalent bonds is a type of bond between atoms share an electron, okay? So kind of all atoms want to fill in their outer shell, and they do this by sharing an electron. Now, in some covalent bonds, they share the electron nicely. That means you have it part of the time, I have it part of the time, they share nicely. In other type of covalent bonds, or polar covalent bonds, one atom, okay, or one substance kind of harbors the electron more than the other, okay? And we know electrons are negatively charged, so if one side harbors it more, has it more than the other side, its net charge will be a little bit more negative than the other side, okay? So an example, a very famous example, is water, right? H2O. And that's why we have hydrogen bonding, because one side of the H2O is a little bit more negative than the other side. So same goes for silicon and oxygen in a crystal. In a quartz crystal, we have silicon and oxygen. The oxygen kind of harbors the electron a bit more, holds it a bit more, so it's more negatively charged than the silicon. Now, in a normal case where we don't put pressure, okay, if we don't put pressure on the crystal, then all the forces cancel out. But if we do put a force, say here, we put a force out. Now here we can see, the atoms, the structure changes a bit, and now we have the top will be minus because we have more minus, and the bottom will be plus, okay? So this is just like, probably a very simplified example, but this is what we had in our textbook to explain how the piezoelectric effect works. Now that we know how sound works, and we also understand the piezoelectric effect, let's dive into the sensor itself and see how we can measure distance. So to start, we need to send out a short burst of ultrasonic sound. Well, how do we do that? Well, inside the sensor, there's a small crystal. Now we said that if we apply a voltage across a crystal, it changes shape, okay? So if we change the voltage 40,000 times per second, we'll get this shape, then this shape, then this shape, then this shape, right? It will change 40,000 times a second, right? If the frequency is 40,000 hertz, okay? That vibration, right, is sound. And if it's at 40,000 times per second, it's ultrasonic, right? Anything over 20,000 hertz is ultrasonic. And that's how the sensor produces an ultrasonic sound, right? It just gives in a 40,000 hertz AC current across a crystal, okay? So it's changing 40,000 times per second. That vibration creates a sound. And that's the sound that leaves the sensor, okay? And number two, the sound travels through the air. We know that. We know the speed of sound travels through the air at around 343 meters per second, depending on the temperature. If it's in water, it will be around 1.5 kilometers per second. Whatever material it's in, it will travel at the speed of sound at that material, okay? It hits an object, then it echoes back, okay? It echoes back, and then four, it reaches the sensor. Now, what happens when the echo reaches the sensor? Well, we said earlier that sound has energy, right? Let me just find that slide. We said that sound has energy, right? And when it comes back with some energy. It loses a lot of energy on the way, as we'll see soon, but it comes back with some energy. That energy squeezes another crystal that's inside the sensor. And we said that if we squeeze a crystal, right, that's the initial piezoelectric effect, we get a voltage, okay? So here we have no squeeze, no voltage. Here we have a squeeze, we have a voltage. So same goes for the ultrasonic sensor. As sound comes back, it has some energy and it squeezes the sensor. It squeezes the crystal. And that squeeze creates a voltage. So now the sensor knows, hey, the sound must have come back, right? Now, how to calculate the distance? Well, if we know how long it took the sound to go and come back, and we do know that because we know when we sent the sound wave, and we know when it hit the crystal back, right, because it created the piezoelectric effect, it created a voltage, we could do distance equals speed of sound, right, times the time of flight to divide by 2. Why do we divide by 2? Well, the time includes the time of the error of the sound going there and back, okay? So to get the distance of only there, we have to divide by 2, okay? That's the reason we divide by 2, okay? Now, why is there a maximum range? Well, I explained this before. We need enough energy to return, to hit the crystal and create the piezoelectric effect. Now, if we double the distance, we lose we only get a 16th of the energy back. We said, right, if we double the radius, we get a quarter, and we're going there and back, so it's a quarter of the quarter, so we get only a 16th. And really, it's even much less than that because a lot of the energy is being dissipated in the air. Okay, so there's only a maximum distance that we could go and still have enough energy on the return to create the piezoelectric effect, okay? So that's the big factor of the distance of these ultrasonic sensors, and especially ultrasonic. For non-ultrasonic, could go further because there's less loss in the air. But ultrasonic, high frequency, very small, wavelength, and we lose a lot of energy in the air. Okay, let's get a little bit into specifics about how this particular sensor works. So on the sensor, there's 3 pins, power, ground, which is self-explanatory, just connected to power and ground. The trigger works like this. The microcontroller will put a 10 microsecond pulse on the trigger. That triggers the 40 kilohertz sound wave, okay? So that sends out the sound. The second the trigger sends out the sound, the echo pin goes high, okay? So it's at 0 volts initially. The second it sends out the sound, the echo pin goes high, goes up to 5 volts, or 3.3, until the sound wave comes back, okay? So it sends it out, it stays high until the sound wave comes back, and the second the sound wave comes back, it goes low. Now, if we measure, and this is really what we do in code, and I'll show you a second how I'll do it with an oscilloscope, if we measure the time that the echo pin was high, we know the time of flight. Okay? We know how long it took the sound wave to go and come back. Now, using the math, we know that the distance equals the speed of sound, okay, times time of flight, which we know because we know how long the echo pin was high, to divide by 2, and that's it. It's very easy. That's how it works, and that's how we could tell distance with a 50-cent piece of equipment. How the ultrasonic sensor works, I thought it would be cool to show how it works in code. So it's actually pretty simple. So you can see here on the top, we designate 2 pins. We have the trigger pin, which sends out the signal, and then the echo pin, which is the pin that stays high as long as the signal did not come back yet. Then in the loop, we trigger the trigger pin for 10 microseconds. That sends out the burst. Once the burst is sent out, the echo pin goes high until the returning signal, and we measure the amount of time here in this line 18. So the time equals the amount of time the echo pin was high, okay? And then for the distance formula, we say distance equals time, okay, which we just got on line 18, times speed of sound to divide by 2. Okay, and then we take that distance and we could display it on the screen or on an LED or LCD or whatever you want. Here we're just using the serial monitor to show the distance that the ultrasonic sensor picks up. So it's pretty simple. And now that we know how it works under the hood, the code makes even more sense. So I want to demonstrate now how we could measure the distance by just using an oscilloscope. So I have here a plate. We'll put it, say, at 40 centimeters. Okay, now the sound will bounce off that plate and go back to the sensor. So let's just pause the oscilloscope and zoom in. Fantastic, and I'll take a picture of that and we'll analyze it together on the computer. So as you can see on channel 2, which is connected to the trigger pin, we have a 10 microsecond pulse, which goes up to 5 volts. Now, as you remember, this is what sends out the sound wave, okay? And once the sound wave goes out, the echo pin, which is channel 1, goes up to 5 volts, okay, till the signal comes back, okay? So let's see how long that took. So each box is 1 millisecond, as you can see here on top. So we have 1 millisecond, 2 milliseconds, 2.2, around 2.35, okay, milliseconds. So let's do the math of what the distance is, okay? So we have 2.35 milliseconds. So to turn it into seconds, let's divide by 1,000, okay? Now let's do times the speed of sound, which is around 343 at room temperature, okay? And then let's divide by 2 to get 0.4 meters, which is 40 centimeters. Isn't that amazing? As you saw in the video, I stretched out a measuring tape and I put the plate exactly on 40 centimeters. And this is exactly what we're getting just by analyzing the signal from the oscilloscope that we get from the sensor. Great, so I want to give one more example. Now let's try even closer. Let's try 20 centimeters. So you put the plate at 20 centimeters and let's catch it. Okay, I'll zoom in and show it to you guys on the computer. Again, we can see on channel 2 the trigger pin, which triggers the sound wave. On channel 1, we could see that it was high for, again, each box is 1 millisecond, so it's 1.2, I would say, is my best guess. So let's do now, I'm gonna get the calculator fully in the screen. Let's do 1.2 milliseconds. To get it into seconds, we need to divide by 1,000 and then times 343 and to divide by 2. And again, unbelievable, 0.20 meters, which is 20 centimeters. So again, just by analyzing the signal we get from the ultrasonic sensor, we could determine the distance.